Hello everyone, my name is Samuel Dembowitz and today I will be talking about the second lab in our physics class, the motion of a falling object. In this video you will see me perform a real-life observation, create two separate computer models in GlowScript, compare the models in a spreadsheet program, and describe the physics phenomena involved. The goals of this lab were to interpret the Newton's second law, which you can see here as the change in momentum over the change in time, with a non-constant net force, where we have gravity acting and the force of drag acting as well, which will be modeled in one of the GlowScript models. We will then use the velocity and position update formulas to iterate our motion over time and analyze the video and tracker and use GlowScript to analyze the motion. The system was a crumpled piece of paper that fell slightly slower than a rock, with a mass of 0.045 kilograms and a diameter of 0.06 meters. I used a basement wall as my testing location, which was 1 meter long, and here is a video of the motion. In Tracker, you can see that there's a calibration stick of the ball and the axes in the negative y direction going downward. I had a 30 frame per second video, so I used those frames to analyze the motion and create this graph up here, which has curvature showing that there is a non-constant net force, which is true for the system. I took the initial position, time range, and found that the initial velocity is 0 in this case due to the ball being at rest. Using the information from Tracker, I was able to initialize two separate GlowScript programs, the first of which only having gravity acting on the ball, with a mass, position, and time range gotten from Tracker. I used the net calculation as force of gravity and the traditional velocity and position update formulas, and here is the GlowScript program with only gravity. You will see the ball moving constant downward with an acceleration due to that curved position graph and the velocity being a constant downward slope since nothing is hindering it. To create a GlowScript program with a drag force included, I had to change my net force acting upon the ball, which not only includes gravity but also the turbulent drag force, which you can see in this equation as 0.5 times the density of air given here, times coefficient b, which we had to approximate after using the computer model over time, which you can see mine right here, times the area of the ball given here, times the magnitude of the velocity squared. I inputted all of this information into my GlowScript program, and you can see it running here. And things to notice is that the position graph looks very similar to the other one. However, the velocity graph reaches a terminal velocity at about 0.2 seconds. Further discussing the terminal velocity, you can see that in the model with drag that it was reached at about 0.2 seconds. However, the one that did not have drag did not reach a terminal velocity. And this is because terminal velocity is when the gravitational force equals the magnitude of the drag force, creating a zero net force. The zero net force means that velocity will be constant. As you can see in this graph, it stays pretty much constant throughout. The terminal velocity will not be made without the drag force, since gravity will act unopposed to the net force, as you can see in that graph. If the velocity was not to be zero at the beginning, then the terminal velocity would have been reached sooner. As you can see in this graph, with a -1 velocity, reached the terminal velocity about 0.1 seconds faster, and this is due to the fact that the magnitude of the velocity is in the drag force equation, meaning that a higher drag force would result in a quicker time to get to the terminal velocity. To create a proper model, I used the positional data from Tracker as well as both of the computer models to create a spreadsheet line graph that you can see here with the observed position, predicted position with gravity, and predicted position with gravity and drag. Towards the beginning, all of the models were fairly similar. However, towards the end, you can see that the model that was closer to real life, the one with drag, was much closer to the final position than the one that was simulated to only have gravity. There are some discrepancies in the observed position, which I believe to have been due to the center of mass being misplaced in the tracker analysis, as well as some movement in the x-axis. To improve the comparison of the ball, I would include a more precise drag force equation when calculating the net force in my GlowScript programs. I would increase the accuracy of the positional data with a better camera with more frames. Extended positional values in Tracker would also allow for better calculations, and creating a chute for the ball to reduce motion in the x-axis and reduce outside interference would also improve the model. When describing the motion of the ball, we can see that there is a constant summation of forces acting upon it. Not only is there gravity and drag, but there are components that are difficult to name in real life that makes it impossible to properly model them in GlowScript. Throughout this lab, we use Newton's second law with constant acceleration of gravity in opposition to the drag force. We use the velocity and position update formulas in GlowScript to properly analyze the motion of the ball. And the applications of this lab are when predicting motion of constant acceleration due to gravity only, when using a basic drag force, and also analyzing the possibility of terminal velocity in a system when the force of gravity is equal to the force of drag in the opposite direction. Thank you very much for watching.